Our next speaker is László, Miklós, Lovász, who is going to talk about algorithmic regularity, Lemmas, and everything.
Thank you for the introduction, for organizing, and for letting me speak. This is joint work with my advisor, Jacob Fox, and his former student, Yufei Zhao. So I'll talk about the regularity lemma and algorithmically, and then the usual regularity lemma, then Frieze-Kannan regularity lemma, and an algorithmic version. And then I'll give sketches of the things that we proved. So Szemerédi's regularity lemma, I'll quickly go over this. Sorry if this is review, but so roughly speaking, it says that in any graph you can partition the vertices into a bounded number of parts, such that between almost all pairs of parts, the graph between them is random-like. So here, for example, we have the partition, and then between these two parts we have some maybe small density. Between these two we have some larger density. And this is a very important tool in graph theory with lots of applications. And it gives a nice rough structural result that holds for all graphs. So to be more precise, let x and y be two sets of vertices in a graph G, and then denote by EXY the number of pairs of vertices in x cross y that have an edge between them. And DXY is normalized, so that's the density between them. And then the definition of an epsilon regular pair is that we have two sets of vertices x and y, and they're epsilon regular if any two subsets x prime, y prime that contain at least an epsilon fraction of the vertices, the density between x prime and y prime is off from the total density between x and y by at most epsilon. So roughly if x and y are epsilon regular for a small epsilon, then the graph between them is random-like, pseudo-random. Now, so to state Szemerédi's regularity lemma, so first for partition, we'll say that it's equitable if the sizes are roughly equal as they can be. And then given an equitable partition, we'll say that this partition is epsilon regular if all but an epsilon fraction of the pairs are epsilon regular. And then Szemerédi's regularity lemma says that for any epsilon, there's an m of epsilon such that for any graph G, there's an equitable epsilon regular partition into at most m of epsilon parts. So let me sketch the proof quickly, because, and then we'll see where it is and isn't algorithmic. So the central notion is the mean square density of a partition. So given a partition, the mean square density is the weighted average based on the sizes of the partitions of the square density between pairs of parts. And this is a value between 0 and 1. And the nice thing is that if we refine a partition, this cannot decrease. You can prove this by, let's say, a Cauchy inequality. And furthermore, what happens is if we have a partition into k parts of a graph, say here, so then if it's not epsilon regular, then we can refine it. So for vi, vj, let's say this pair is not epsilon regular, then we take the pair of bad sets and we refine vi by this bad set and vj by this bad set. And then maybe vi is also not epsilon regular with some other vk. So then we take this pair of bad sets and refine it further. So in this way, we've divided each part of the original partition, if it had k parts, into at most 2 to the k plus 1 parts. And you can show using a Cauchy defect inequality that in this way the mean square density will increase by epsilon to the 5th. So then the way the proof goes is you take a partition, maybe trivial partition or a small partition, you check if it's epsilon regular. If it is, you're done. If it's not, then we refine it and then slightly refine it further to make it equitable. And then we keep iterating this, and this can only happen 1 over epsilon to the 5 times. After that many steps, you must end up with an epsilon regular partition. And so what does this give for m of epsilon? So you get an exponential in the number of parts in each step, so it gives a tower function. So if we let t of n be 2 to the 2 to the 2 n times, then this gives m of epsilon is at most tower epsilon to the minus 5. And Gowers and later subsequent work, well, Gowers showed and subsequent work improved that upon the fact that you actually need a tower function here as a lower bound on m of epsilon. Okay, so how can we make this regular? Well, the main challenge is if we have 2 sets x and y, how do we check if it's regular, or how do we find a pair that's not regular? Because you can't just check all subsets. If you can, that's the basic problem to solve, because then you can do the same proof by taking the bad sets and refining. So Allen, Duke, Leffman, Riddle, and Yuster showed that if a pair xy is not epsilon regular, then they can find a pair of subsets that show that they're not epsilon to the 4 regular. They do this by basically observing that, so a pair is epsilon regular, a pair being epsilon regular is up to changing epsilon by something equivalent to the C4 count between the 2 sets being not being close to what you would expect in a random graph. And the C4 count, then you can, the C4 count between x and y is kind of the trace of AAA transpose. And so this gives an algorithm which runs in time O epsilon n to the omega plus little o1, where omega is the matrix multiplication constant, which is known to be less than 2.373. So Frieze-Kannan also gave an algorithmic proof through a spectral approach looking at the singular values. Now, this was improved by Koayakawa, Riddle, and Toma, who gave a n-squared algorithmic lemma by basically showing that you can find a good expander graph and test along edges just in that expander the codegree condition, which is another equivalent condition to the C4 count. And another result in this area is Alon and Naor have an algorithm, a polynomial time algorithm, which can approximate the cut norm, I'll say what that is later, up to a constant factor. And they use this to get a polynomial time algorithm with T O of epsilon to the minus 7 parts. So here, even though, so in the regularity lemma, of course, we know that a tower is necessary if you want it for all graphs, but many graphs actually have a much smaller regularity partition. Most graphs even, by some sense. And the previous algorithms, there's no guarantee that even if the graph has a small one, they would find it. So to look at this problem, Fisher, Matzliach, and Shapira give a randomized algorithm which runs in constant time for a fixed epsilon and k, and that if the algorithm has the property that if the graph has an epsilon regular partition with k parts, it finds a 2 epsilon regular partition into at most k parts. Yes?
How does it return an answer in constant time?
Yeah, so this constant time means if you're okay with it being implicitly defined, then it runs in constant time. Otherwise, you multiply it by n, and then you have the partition. And related to this is this kind of folklore that's written down in a blog post of Terry Tao, which is a randomized algorithm for the regularity lemma that runs in constant time and gives an epsilon regular partition. Basically, it samples a random set of points from the graph, and then your partition is basically how the points are connected to this fixed random set. So that's why it's implicitly defined by just this set of random points. So our result for this is a n squared time deterministic algorithm. So these are randomized algorithms. Our result is a deterministic algorithm which also basically does the same thing. So if there's an epsilon regular partition on k with k parts, then we find a slightly worse partition into k parts for any fixed alpha. We can do it in n squared time. And an intermediate result towards this is a result to test the regularity for a single pair of parts. So we give a deterministic algorithm which, given epsilon and alpha and a graph G between x and y, outputs either that this pair is epsilon regular, or it gives a pair of subsets that show that they're not slightly worse at 1 minus alpha times epsilon regular.
Yes. There's no K in the big O in the first theorem, but there's a K in the big O in the second theorem. Is it by mistake?
Oh yeah, sorry. Yes,
Oh,
sorry. Sorry, so that K should be there and not there. Thanks. Okay, so because of the large number of parts in the regularity lemma, there are other versions have been developed. So there's the Frieze-Kannan regularity lemma, also called the weak regularity lemma. So given a partition of the set of vertices, we say that it's Frieze-Kannan epsilon regular if for any pair of sets S and T, the number of edges between S and T is close to the number of edges you would expect between S and T, kind of if all you knew about S and T is their sizes and their sizes inside each of the parts of the partition, right? Because then you would expect between S, for each I and J, you would expect this many edges between these two sets. So if this count is off by at most epsilon times v squared, then we say that the partition is Frieze-Kannan epsilon regular. And then the Frieze-Kannan regularity lemma says that for any epsilon greater than 0, every graph has a Frieze-Kannan epsilon regular partition into at most an exponential in epsilon, polyepsilon number of parts. And here, I'm not concentrating on this, but you can also require this to be equitable. And the proof of this is similar, except now instead of refining for each pair by the worst case, you refine by a single pair of sets globally. So you have globally in S and T. So if you have a partition that's not Frieze-Kannan regular, you globally have a pair of sets whose densities are off, and you refine by that pair, and you can show that the mean square density increases by epsilon squared. And you get a factor of 4 in the number of parts. So here, basically this partition, so this property of the partition is weaker, but in exchange we get a much smaller regular partition. So a common application, it's common in applications of the regularity lemma to combine it with the counting lemma. So to state the version that we use, it's easiest to state if we first define this notion of cut distance. So if we have two graphs, G1 and G2, on the same vertex set, we define their cut distance as the maximum over pairs of sets of the difference between the number of edges between them normalized to be between 0 and 1. And in this language, a partition P is Frieze-Kannan epsilon regular. It's if and only if the cut distance of G from this other graph, GP, where GP is defined as, so let's say we have a partition of the vertex set, and then between, so let's say parts VI and VJ, we have weighted edges weight the density between Vi and Vj. And you do this for all pairs of parts, including within parts. So the partition is Frieze-Kannan epsilon regular if and only if the cut distance between these two graphs is small. And then in this language, the counting lemma says that for any graph on k vertices, if you don't know what the homomorphism count is, you could basically think of it as the number of copies of h and g up to a lower order term. So the difference between the number of copies of h in one and the other is bounded by the number of edges in h times their cut distance times n to the k. So now how can this be made algorithmic? There are two results due to Delamonica, Kalyana, Sundara, Martin, Rudel, and Shapira in this direction. So first, they give a deterministic algorithm which finds a Frieze-Kannan epsilon regular partition in time polynomial in epsilon times n to the omega. And in a later work, double exponential in epsilon and n squared. So you reduce omega to n squared here at the cost of worse dependence on epsilon. And the main tool for the main meat of the problem is finding the bad pairs. So for example, for the first result, what they do is they show that there's an n to the omega plus little 1 time algorithm, which given an epsilon and an n vertex graph and a partition of the vertices, it either correctly states that this partition is Frieze-Kannan epsilon regular, or it finds a pair of sets which show that it's not epsilon cubed regular. And in this result, there's an analogous statement for n squared. And so what this means is that we can say a bit more. We can say that there's a polynomial in epsilon n to the omega type algorithm, which given an epsilon and n vertex graph outputs a t, a polynomial, and pairs of sets, SITI with CI, such that we have this, such that our graph is in cut distance very close to being this other weighted graph, which has this short description, where you start with every edge having the average weight in G, and then you add, the CI may be negative, but you add just these K SITI between them. So you add these bipartite graphs between SI and TI. And we can also here decrease omega to 2 at the cost of a worse dependence on epsilon.
Excuse me, is this sets S and T are disjoint?
You can say that they're not disjoint, and then this K SITI you have to define properly. You can also just multiply it by 3, I think, and then make them disjoint. Okay, so what we apply this to is a problem of counting subgraphs. So the basic algorithmic problem is we're given a large graph G and a small graph H, and can we count the number of copies of H in G? Now, doing this exactly is NP hard. In fact, just checking whether there's a single copy is NP hard. In fact, so in this direction, Zuckerman showed that it's NP hard to approximate, let's say H is a clique. Even if you want to just approximate the size of the largest clique within a factor of n to the 1 minus epsilon, this is NP hard. This was shown building on an earlier result of Hastad. So what we look at is, okay, so how fast can we approximate this if we allow an additive error of E epsilon times n to the VH? So if H is on k vertices, G is on n vertices, then we want to count the number of copies of h in the graph with an error of at most epsilon times n to the k. So if you allow randomized algorithms, there's a pretty simple algorithm here, which is just you sample k sets of vertices and you keep repeating that 10 over epsilon squared times. This is a binomial distribution, and so it's highly concentrated if you take it large enough. So with high probability, it'll be within epsilon. The fraction of times you see h in a random k sample will be within epsilon of the total fraction of h. So, but what about deterministic algorithms? So you can use algorithmic regularity lemma. And so if you use the usual regularity lemma, you could get a regular partition, and then you can use the densities in that regularity partition to count the copies of h. So Duke, Lefman, and Rudel developed a different version of a weak regularity lemma and use this to show that it can be done in time n to the omega times exponential in k over epsilon. And what we show is that this can be done in time for a fixed h polynomial in epsilon and n. So for example, what this means is we can count the number of copies of k1000 with an additive error n to the 1000 minus 1 over 1 million in time big O n to the 2.4. Okay, let me now, in the time remaining, sketch our proofs. So let's look at the counting subgraphs first. So we apply Algorithmic Frieze-Kannan here, and that's where so for that term, the algorithm takes that long, and we get this graph G prime, which has this nice structure, and the cut distance of G from G prime is at most epsilon divided by the number of edges of H. And so by the algorithmic Frieze-Kannan, we can guarantee that T is at most a polynomial in epsilon. And what this means is that the count of H in G and in G prime is off by at most epsilon times n to the k. So we can just count the number of copies of H in G prime. And to do that, because we have this nice form, we basically do the graph version of the distributive property. So we compute this home H G prime by computing a sum of t plus 1 to the EH terms, where each term corresponds to assigning each edge of H to one of these terms. And it's a kind of weighted, like multicolored edge homomorphism density. So I don't want to go into details, but I hope the main idea here is clear. So now let me sketch the proof of the other result. So first, this testing regularity between a pair of sets, x and y, with a small interval of error. So again, we apply the algorithmic Frieze-Kannan regularity lemma with distance alpha times epsilon cubed over 4. So we obtain a graph G prime at that distance. And what this basically, because of how we've chosen this distance, the bound on the cut distance, we can work with G prime in the sense that the kind of how regular they are is off by at most alpha epsilon over 4. So we slightly decrease this interval. Instead of epsilon and 1 minus alpha times epsilon, it's 1 minus alpha over 4 times epsilon and 1 minus 3/4 alpha times epsilon, and then we work with G prime. And now for G prime, so how do we test this for G prime? So we have big sets x and y. So now suppose we have U subset x and W subset y. So in order to determine the density between U and W, in G prime, we only need to know the size of U, the size of W, and the size of each U intersect SI, and the size of each W intersect TI. Because then if we have all of these values, we can plug it into this formula and check the density. So now we can't check it for every single intersection size, but we can take a net of possible intersection sizes, a bounded net, and check for all of those. And so for each point in this kind of net, we have to check two things. First, we have to check whether it's feasible, so whether there actually exists a U and W with those sizes and intersection sizes. And second, whether the density is off. So there are some details I'm skipping over here, but this is the basic idea. And then to apply this to get a small regularity partition. Oh, sorry. So as a corollary of this result, we can also, for a fixed k, we can check regularity of a partition of size k with, again, a small interval of error, so between epsilon and 1 plus alpha times epsilon. So now to finish the proof of finding a regular partition without most k parts. So again, we apply the Algorithmic Frieze-Kannan regularity lemma. And here, again, we choose the distance so that we can work with regular partitions of G prime instead of G. And so again, this will, if we switch from G to G prime, the way we've chosen the distance, how regular the possible k-part partitions are can change by at most alpha epsilon over 4. And then in G prime, the only thing that matters for a k-part partition that's a candidate to be regular is how it divides up each part of the Frieze-Kannan partition. So again, we take a net of possible size of partitions, k partitions, and for each point in this net, we apply the previous algorithm to check whether its regularity, to check its regularity between 1 plus alpha over 2 epsilon and 1 plus 3 alpha over 4 epsilon. And at some point, we must get that it's regular, and then that means it must be slightly worsely regular for G. So again, I'm skipping over details here, but this is the basic idea of the proof. So to summarize, we use this, so there's this algorithmic Frieze-Kannan regularity lemma, two versions due to Delamonica, Kalyana, Sundara, Martin, Rudel, and Shapira. And we use this finite sum structure. This is true just in general for the weak regularity lemma, that it gives this finite sum structure in addition to just the partition. And we can use this to count the number of copies of a small graph H in a graph G efficiently. And we can also use this to more efficiently find and test the regularity of sets and of partitions. So some open questions here. This was posed yesterday as well in the open problem session. Can we get a faster Frieze-Kannan regularity lemma? And another open question is if we're counting the number of copies of H in a graph G, so we did it with epsilon n to the k error, can you do it with a smaller error like n to the k half, or can you prove that you can't have a smaller error? And I'll finish here. Thank you for your attention.
Questions? So you mentioned that there is a randomized one that is in constant time, right?
Yeah.
So is there a chance of doing something similar by randomizing?
Well, so if you have constant time, then you can't explore, you can only explore constant.
So I suppose you need to sample a constant controversial set.
Yeah, but I think there should always be a small probability that it's you got a very unlucky sample.
Well, I guess another way of saying it is like in terms of your added error question, like if you want to count like copies of H, and then that has like n of H number of vertices or something. I mean, you can like that's some sampling process, and if you there's only so many graphs, so if you took it seems like essentially there should be a set of subsets that you can just probe, not necessarily a constant number, but a polynomial number, and that would give you an additive error, which is where the exponent additive error isn't so bad as in your results. It may be a worse polynomial. I don't know if you can construct those explicitly, but it seems like that should be possible.
Maybe.